So I'm going to make a subsystem like this. So exciter, generator, that's one block. I think I did it last time. So on Python 1, simulate browser. So I'm making the subsystem. Someone use it. There should be some subsystem here. Subsystem. So I call this is genset. So I'm going to generate this subsystem one more time. So Control C. Subsystem here. So this is EF, and this is EFD. Okay. And inside here, this is exciter. So I'm going to have this is exciter. Inside here, there is gain block here. And there is integrator block is there. And there should be some block here somewhere. Some. Right here, some. Okay? So I'm going to add here, connect to this one. And this should be plus and minus. So I'm changing this one to minus. And there is another gain here, Control C and V. So I'm going to say this one is a flip. So to here, flip block here. Okay. So this goes to here, and this goes to here. So now matter of the gain. So I change this is KE plus as just name. Okay. And this will be 1 over TE. 1 over TE. This is just name, so it doesn't matter. So this will be 1 over 0.5. Now, my case is 0.2, so I'm going to make 0.2. Alright? 1 over 0.2. Over here. And integrator. Now I can get rid of the obvious integrator, so I can hide the name. So that's what I have. So I generate one block. Yes.
Say, well, 1 over 0.2, that's like just 5, but I'm thinking you're looking at 0.2 in there just so you can see that's where the time constant goes.
Time constant is 1 over TE is time constant.
Mm-hmm.
So time constant is 0.2. That's why it's 1 over 20. Okay? Any problem? Yes.
Like KE plus SE, is that a label?
This is label, just label, name. If you don't stop me, then I'm going to keep going this side. So this is exciter. Okay?
One more second.
Please go back.
Go back again.
Yeah.
The feedback gain is just one, right?
That's just one.
Yeah.
How did you establish the node at the output of the sum of the integrator that ties into the gain?
Just connect it from here to
The
here.
node right here, right after the integrator.
That's the integrator. This is the label, output.
Drag it from the
Drag it, just drag it.
Drag it.
Yeah.
from the other side.
You connect it from, yeah, no, not that way. Because it's just going to here, right?
Okay, thank you.
Yes.
Your in ones and amount ones, do those become EED and EFD?
Yes, I have to change that one. Yeah, that's right. I missed that one. That should be EEF. That should be EF. That's name. Okay. So I construct one block inside. That is inside here. Okay?
Okay.
Everybody get it? Okay, then inside here. So inside here, this one is here. So I'm going to make another one here. Wait a minute, what? Excited is here. This is excited. And so now, genset is actually not like that. This is not the way. So here, this is, I got it here. I have another block. For generator, genset is not EFT, that should be VT, right? VT. Because generator out. So I'm going to make another block. Now I'm going to make a copy and paste it. So I'm going to have it here. This is a generator. And this should be EEF instead of EEF, EFT, and this is VT. The same name here. So change this one first, and change this one again. And this is T prime D0, right? Prime D0. And I selected this one to 4. 4. So name is just, you don't need this one. So it's a hide name. That should be okay. In fact, you don't need this one, right? For generator, it's not like this. So I have to generate this one. So I have to do different ways. Okay? Sorry, I'm going to have genset here. I need to construct this way, right? So this is the EFD, this is the disturbance. So I'm going to make one more. So let's first of all get rid of this one, mark it this one. So now this one, I added this one more. Control C, Control V. So this is IT. And there is gain here. Control C, Control V. I'm going to exactly the same way. So let me move this one a little bit. Move this one to here. This should be plus minus, minus plus. Minus plus minus. Is it minus plus minus? No, plus minus minus. So it should plus and one more minus. So I have to, that's not the way to do it. So now instead of the round, I can do that. Same thing.
That's okay.
Now I'm going to move to here. So there is a feedback first of all. Okay. So now this one is EFD. EFD force. And second one is yes. And IT is here. I'll get back to you. So here, so it should be ST minus XT prime. That's gain. ST minus X prime T. So it should be 1.85 and 0.81 minus 0.3.
1.81 minus 0.03.
0.3. So basically same thing. You can do the round too. If you don't like this one, just change it. The round. Round. And if you get it, this one probably is okay.
Dr. Kim,
Yes.
ours didn't allow us to name that EFD because it already exists on the other one.
You just rename it.
Okay. Just name the EFD
Yeah,
once.
rename it and change it back. So it doesn't matter.
Okay.
So as long as it has EFD and IT, then it's okay. So this is this double part. This one is actually closure up here. Okay?
Mr. Kim,
Yes.
what you did there was, you copied what was inside the exciter system and called it a generator, right? Is that what you did?
Yes, that's how I did it here. Let's go back here. This is a genset. Now you have it here. So there's the exciter. The exciter is like this. Okay? And generator is like this.
Dr. Kim?
Yes.
Is it a IT for your second input to the generator?
Hmm? Yeah, second input. I made this one to in here. IT is number one, so that's why it's top. I can make it. I change it. So let's do it this way. So instead of this is number one. So I'm going to make one, and actually you remove this one, then this becomes one. So now add one more thing. Control C, Control V, and change this one to EFD. Then exactly the same thing. Right? What happened here? Yeah. That's exactly the same thing, right?
Quick question.
I'm curious about what you put in your gain triangle there. Is that 1.8 minus 0?
1.8, 1 minus 0.3. Just, you can make this just because this is just XD is 1.81. X prime D is 0.3, that's why. It's a one generator system. So EFD should be right here. You output it here. So this is the disturbance part. So now you have complete pop the point here. Okay? So now I'm going to make input, another input not here. Let me go to project here, how I did it here. Either way you can do it here. Okay, so that's why you have it here. So this is the red one, the yellow one, so I'm going to make the yellow. So this whole thing, not this one is the yellow. So I go, why only yellow one? Should be two. Okay, now first of all let's do here. Background, yeah. This one should have two inputs. So copy, Control C, Control V. This is the IT. So once you got there, I told you that. So you have IT and EFD. IT is the second or first? I'm going to go exactly the same thing, so let's go here. IT is the top. So I'm going to have change the name. So it should be remove this one first. No, remove this one first. And copy. So let's change the sequence. So this is the EFD. So you can change it here. So genset is IT, EFD, and VT, right? Everybody got that so far?
Can I adjust the lights? Can I adjust the lights? No. The lights, can I adjust it?
Yeah, sure.
All right.
Better?
Yeah, much better.
You should have seen it before. And if you've done it, you're halfway done actually. That's the easy. So simulation is very easy to do. So now I will show everybody like this. Okay, I'm going to rename this one to project number 1. Save as. Okay, project number 1. Do I have project number 1 or not? Oh, I don't have it. So let's have project number 1. Project 2013. How about that? So this is my friend. This is generator. Later you want to change time constant, just click here inside. There is the exciter, you can change the 0.2 to whatever it is, right? And you can change the generator time constant, just change the, instead of 4, 1/6, like that, right? So it's nothing changed. So once you got this one, then you can change your system 1 to 3 based on time constant T.
Dr.
To, yes,
Did you say 0.4 or 4?
I said 4, right?
That was 0.4.
Did I say 0.4?
I don't know.
So 4.
0.4?
4.
Oh, sorry.
Yeah, time constant, the generator is slow, so it's a 4. Usually generator, small generator is about 1 second. Like a hydro big generator is about 10 seconds. Most of a steam turbine, like a generator, huge turbine like the size of this house, this classroom, it's about 4 seconds.
This may just be like some semantic issue, but like I noticed for the exciter that you set the time constant at 0.2. If you want to do the null value, it was 0.5 before. I didn't know if you, well, because we don't have to, we can just use like a new value. It's
Yeah,
not-
new value, because this is my case.
Oh,
This is my case. Okay?
okay, sorry.
So you guys have to change it.
Oh.
Okay? So I show the example as example. Okay? So now we are done with number 1. So you generate input and output here. Okay? And transfer function of this one, this is a theoretical, you can do it, right? So probably obvious into it, right? So I'm going to have for this one. Okay, feed forward, right? 1/0.5.
Can you write a little bit, please?
That's why I already saved this one. So I will show the one example here. This one. 1/0.5, 4 to pass. A point. This example is 0.5, right? 1/0.5. 1/s. This is 4 to pass. 1 cross this whole thing. So it will be 1 times 1/0.5, 1/s. So you multiply 0.5s, so it's going to be 0.5s plus 1 and 1. That's a transfer function. Okay? So unit step apply. You find the transfer function, right? And then plot the input output when the unit step apply without the disturbance. So IT equals 0. So we're going to have here unit step, apply unit step. So now I'm going to have input. So go to Simulink. There is a source. Source here. So it will be unit step, so I'm going to use here.
Dr. Kim,
Yes,
where did your IT input come from, genset, subsystem?
okay, go back to here. IT is here, going to the generator, inside the generator is like this.
Okay, thank you.
Alright?
Yep.
So IT make 0, so I'm going to make Control C, Control V. So it's 0, make it 0. So now how to make it 0? It is step time is 1, which is step time 1. Initial is 0, final is 0, so all the time 0, no matter 1, right? So the step is obvious, so I'm going to get rid of, clean up a little bit, hide the name, and let's hide the name. Or unit step, you can make input, and this one is show name, and change to this one, to disturbance. Okay? And I can change it actually. Flip the name, so it will go up here. Now, response. Response will be here, where is it? Yeah, sync. Should be scope. So now this one is from the input to scope. That means this is the VT, generator output. So I'm going to make a VT here. That's I'm going to measure here. Now, if I run this one, that means there is inside the exciter is there generator. So your response will be from EF to VT. Okay? You got it? So this one is actually from EF to EFD, EF to the VT, I to the VT, and EF to VT. I'm doing this one now. Okay? The last one I'm doing. Yes.
For the transfer function that when you're calculating for VTS versus ITS in step 2, do we assume that in that case that that the input EEF is 0?
Yes.
Okay, just making sure.
Yes. So what I'm doing is last part, this guy. Okay? So just run this one. So your response will be like this, right? So it's so slow, so I can make it like 30. And remember, you're gonna copy and paste this one, so make sure, change it. This one to graph. Good. Here, and make this one to that color. Or I like this one. So you can have it. Why I don't background?
Figure.
Yeah. Figure background is this guy. It should be. This is the axis. So
Yeah.
line. This one? No, it's not. What is it?
I think it's like this.
You gotta change the axis black to white.
White here.
And that one should be black.
This guy. What is it, this one? This one is axis?
Yeah, change that to black. Should be alright.
No?
Yeah, that first one.
Yeah, you
the
should
First blue next to figure needs to be
figure.
black.
This one?
Nah, the figure.
This
Yeah,
one is
change
black?
that one.
Or no, white, black.
Yeah, you can change to.
I can
No,
see- I
change
can
the,
see it out here.
You gotta change the figure.
So what I have here, So I can
See,
take
that's
background
over
is
there.
blue.
Yes.
If you make that figure,
Yeah.
that one, if you make that one white, it gets rid of it.
Why?
And that's it.
You see,
Yeah, yeah, that's it.
Like that, right there. There you go.
so you can use this one, okay? Then you can copy and paste this one. Actually, I don't know what you guys are using. Usually I use the
Snippet.
capture. So you guys have a capture region? So
Like her right here.
Yeah, that snippet.
what about similar to this one? So it doesn't matter whatever you use it, but don't use. Because most figure, when you show the figure, you have to make it clear, okay? Some of the yellow is here, I cannot see it. So don't do that, okay? And there is a step response. Usually I have -5 points. Step response. Some people doing like this. You have to zoom in, so make it reasonable way. Right? This is -5 point. Make sure, okay? Okay, so I show number this one. How to show this guy? E, F, D, E, F. Same thing you can do it here. Here, instead of this output, I can delete it. I can make it temporarily. Right here. And this is exciter. Exciter response. So it's a fast, as you can see. It's very fast, right? So you can do that. So you can play around. You can control the what output I'm going to see. Okay? Any questions so far? So that's I showed it all. 1, 2, 3 I showed it.
It's just when we do it, you're going to want the input compared to it, right? Because it's plot input and output, so I didn't know if we needed a mux.
Yes.
Okay.
That'll be better. Okay? Any questions? Yes.
Can I see what's inside your generator?
Huh? You still have a problem this one?
Did you get rid of the amplifier that used to be there, the KE plus SC, or does that not need to be there?
It's not there. Okay. So next thing I should use to is number 4. So what is number 4 is doing? So now let's go back to project. This one is here. So repeat the 3 with the load applied. Okay. Now this time the load is like 0.1 and 0.5. So I'm going to make a load is 0.5. Look at here. 30 seconds I did it, okay? Now, your step input is, first of all, let's look at this one. Not like this, okay? This is the 1. So, if you have 1, there is no state error here, right? It goes to 1. No state error, right? So now, I'm going to disturbance about 20 seconds later, I'm going to add the disturbance. So 20 seconds later, I'm going to add disturbance about 0.5. Okay? That's what I mean here. So let's make this one about 50 seconds. Okay? So now you learn this guy, what happened here. See, without the disturbance, it goes to 1. With the disturbance, it goes to some value here, right? So what is the value here? You can theoretically find what is the value is this guy. So about 0.245, right? Got it? So when you apply the disturbance, there is a state error this much. Lots of state error you see. So from here, this is a state error because of disturbance. Okay? So how to compensate this one? So the problem is, so discuss what you have to do to reduce this state error. Okay? So how are you gonna do it? How are you gonna make it even if the state disturbance is here?
Integrated feedback?
Hmm?
Integrated feedback?
Not yet. That is number 5.
Feedback from the disturbance.
You're not supposed to use feedback. So yes,
Change the step time step?
yeah. Change the step response on them. If it's a disturbance, you need to compensate in the step input. Right? So for example, this is about the point 7. So let's add it here. So I'm going to here. So there is this, you know there is some disturbance. That means you have to change this one to like 1.8. Oh, sorry, not this one. Okay? So run this guy, approximately. Let's go here. So it goes close to 1 here, right? So basically you need to change the step input, right?
You want it to be close to 1, right?
Yeah, it should be. Even if there is disturbance, you have to change it to, somehow you need to change it to step input and maintain the 1. Actually, it goes to 1.7, something like that, then it's probably almost there. Let's have here.
Dr. Kim,
Yes,
can I see your,
about that level.
can I see your disturbance values you have set up? Can I see what you have set for your disturbance values?
Disturbance? I want to see the effect of disturbance. So initially it was 0. After 2 second later, it will go to 0.5. Right? This is what happens usually. Long time ago, what I mean is, first time you have a generator. Input is fixed. Input, they don't change. So somebody used some motor, or it's cold day, they are adding air conditioner, whatever it is. Because load is increased, the current is increased, then voltage will drop. So long time ago, they need to just monitor the output, increase step input to maintain the 1. That is a manual mode. Okay, we call the manual mode. That's what we do if we don't have a closed loop. Okay? So that's why we are running the closed loop control system. So if you don't have a closed loop to adjust this one, somehow you need to change the step input. Automatically change the step input. That is the feedback system. Okay? Here, so that is number 4. The time constant actually affected this one. I'll leave it for you guys. What is your guess?
No.
Yes.
Yes and no, so have. Actually, it should not. Check it out, okay? Time constant is nothing to do with the state, okay? Okay. So now, number 5. Make a close loop here, okay? And what I need to do, close loop is only KP like this. 1 KP, all right? And make a closed loop here. So I'm going to make a closed loop here. Project number 1. Okay, now let's make a closed loop here. So let's go to simulate here. There should be some block here. Somewhere, some block. Commonly use some block here. here, it should be negative feedback, so it should be minus. If your system is unstable, check it out immediately. It's a negative feedback or not. It should be negative feedback. And there is a gain here, simple gain. Okay. So let's move to here. Not here. So let's call this is KP. Okay? So now, first of all, what is the problem here? See here. You have constructed closed loop, state theta, find the state theta, rising time, settling time, and closing time. So first of all, let's assume Kp is 40. Okay? So let's have disturbance initially make it 0. So 0 here. Now I'm going to make this one is a 40. Now, I told you before, if it's a Kp is increased, effectively your time constant, effective time constant to change, right?
Yep.
So how much? If it's a 2, your effective time constant twice fast. 10, 10 times fast. 40, 40 times fast. Okay? So now I don't need, actually you can learn here, you can see that. Before it was slow like this, actually slow response like this, right? This is step response because there is no disturbance. It's like this. Now look at here. Actually I have to change the step input to 1.02. So now run this guy. How long does it take before? It was about 20. That's the state almost about more than 20 seconds. That means now if you do here, actually it's too much, so I'm going to have 5. Look at that. So it's 0 is about actually the rising time is somewhere here, so about 0.5 seconds goes up, right? Now, look at here, this one is like a less sample, here, here, here. The sampling is a problem, so I'm going to change sampling time to this one to 0.01. One change, and then rest of it will follow that. Go to here. So we have a nice response there. Okay? Yes.
What did you just change to 0.001?
Sampling time. Yeah. I'm going to show here one more time. Input 0.01.
Thank you.
And there is, the other one is -1. That means it's inherited. So previously 0.01, it will follow that. Okay, that's what I meant. So if you select 1, it's okay. So your response is here. Now, one bad thing of a closed loop is, if it's open loop, no disturbance, you apply the 1, output is 1, right? I made a closed loop, then depends on the closed loop gain, you have state error there. Okay? That is the only bad thing. When you have a closed loop, that is a good thing, because you don't have to adjust manually. So automatically do that. On the other hand, two bad thing is, it can be some error, state error. Another one is, it can be unstable, because it's a closed loop. Okay? So we'll see later. So it's a closed loop. There's a good thing and bad thing. Good thing is you can make it faster, and you can more robust control. But on the other hand, there is always stability issue there. So now, if it's a 40, I have this much error here. Okay? Now, why this much error? Actually, I showed that one in here. Last time, investigate one more time here. So how much error you have here? About 0.975, so it's a 0.25, right? That's approximately right? So 1 divided by your error will be 1 divided by 1 plus 40. So it's a 0.024. So 1 minus, that's the error. So it will be 0.9756. That's exactly what I have. 0.9756 is here. Okay? The theoretical value is matched with that. Alright? So now I can increase here. Give it one more time. Let's k equal 10. Kp equal 10. Here. Let's make it 10. If it's a 10, it's got to be slow a little bit. But what is the error here? Actually, it should be about 0.91, right? 0.89 something. That should be how you calculate 1 minus 1 divided by 1 minus 1 divided by error. Error will be 1 plus 10, right? That is the error. Second term is error. This is the error, right? So 1 minus this one here will be 0.9091. So that is 0.9091. Okay? So it's gain. Theoretically, you can find your state error. Okay? Yes.
So using the game, you can find the space error?
You can find the state error and then find if your response is right there or not. Okay? And theoretically, how you got it is showed in the slide. Okay? So that's what you have to remember. Okay? So what is the next one? So now, good thing is, okay, now, because it's asking 40, so I'm going to select some value. For, as an example, I'm going to make it like 50, for example. So your response here, based on this one, you can find maximum overshoot, rising time, right? Settling times, you can find it. Actually, there should be some you can find the minimum and maximum. Actually, there is way to do it. I'll probably let you know later. Okay? So that's number 5. So you can find settling time, rising time, damping ratio, maximum overshoot, and here. Now still, if it's a KP right here, your system is one over T S plus 1, 1 over T prime D0. Okay, let's use number. Number is easier to do. S plus 1, 2S plus 1, for example, here. And there is gain is 50, and plus minus here. So your transfer function, closed loop transfer function, closed loop. Okay? It will be 50 divided by S plus 1, 2S plus 1, divided by 1 plus 50, S plus 1, 2S plus 1, right? So it will be S square plus 2S square, 3S
51.
plus 51 over, no, 50 over this. So now, this is, second order system. Now, based on, I can make it this one too, standard form, okay? It means divide by 2 both sides, top and bottom, so it will be 25, that's square, and 1.5, s plus 51 over 2. So this will be omega n square. So this will be 2 omega n
W, yeah.
omega zeta omega n. So you can find zeta, you can find omega n. Actually omega n will be 51 over 2, square root of that. Right? So basically you know that, then there is, you can find definition. That's what we have here. Yeah. So you can find all over rising time, peak time, like that, right? If you know that. Because it's a function of omega n and zeta. And omega d is defined like this. So as long as you know the omega n and zeta, you'll find overshoot and damping ratio. Right? That's your frequency like that. Okay? So now let's go to the next one. So you find this guy. So you're done with the number 5. Now find the pole and zero, open loop system and closed loop.